So, Mauricio, do you hear me?
Yes, I can hear
Okay,
you.
perfect. And then the presentation, do you see?
Yes, I see. I see the presentation in full screen.
It's called Lisp eller Lisan? Nej.
There's no place to sit down.
Nej.
Back. Alex Captisco. Just leave there. I mean, I can see people can say.
كيف حالك؟ مظبوط. Is it okay? I just say Carlos de Souza.
Yeah,
It's okay.
it's okay. No, say the full name. Carlos de Souza is fine.
All right, it's time to start.
Okay.
So good morning, everyone, and very welcome to trial lecture of Mr. Carlos de Souza. Carlos has been a PhD candidate at our department under the supervision of my colleagues, Professor Erin Baczynski-Pulik and Professor Jengao. He submitted his thesis to the faculty, and then faculty appointed committee. The committee, the first opponent is Professor Finn Gunnar Nilsson from the University of Bergen, and Professor Maurizio Collo from Strathclyde. Professor Collo, if you hear us, you would like to say hello to the audience?
Hi, everyone. Good morning. Good morning, Carlos.
Yes, good morning. And then myself from Marine Department, Amir Nejad. Carlos has been given a topic for trial lecture 2 weeks ago. So he will give first trial lecture, 45 minutes, and now floor is yours, Carlos.
Thank you. Okay, so good morning, everyone. Thanks for coming for my trial lecture. I was assigned the topic on multipurpose voting platforms, design and analysis, which I myself find very interesting. So I'll start with an introduction with this common definitions and objectives, and then I'll narrow to the scope, and then I'll talk a bit of background, design, analysis, and final considerations. So the term multipurpose floating platforms, here it's meant to mean 2 or more offshore industries integrated in the same platform. So that could be anywhere in energy production or harvesting, food production, mining, logistics, leisure, etc. The main goal here is to reduce capital and operational expenditures. So the idea is that by sharing the same infrastructure, you're saving costs, and also saving costs with maintenance, installation, decommission. But also you can try to improve the overall outcome of both activities by exploring synergies between them. So a good example here is when you have wind and wave energy production at the same time, So you can, in a way, combine both to have a more smooth power output rather than large variations. And also, for example, supply energy for a fish farming facility. And also it's intended to reduce environmental and societal impact by optimization, the exploitation of marine space, and reducing conflicts. So the scope here is multi-industry rather than multi-activity. For example, an FPSO would be an example of a platform that encompasses many activities, but it's not main industry because all the activities are serving the oil industry. So here I'm talking more about like different industries. So wind energy and wave energy and fish farming, for example. And I'm focusing on renewable energy plus fish farming because that's it seems to be what's attracting most attention of all the researchers lately and industry. And there is a vast amount of publications and projects. I'm talking about multi-purpose platforms in single blocks rather than modular platforms. And I'm sticking to preliminary design analysis because this is a non-established industry. We don't have any example of a commercial and successful platform yet. So it's not the time to go for detail on designing and cost effectiveness analysis and those things. Okay, so I think it's interesting to see some of the previous projects and concepts. The European Union has funded a number of projects in this topic. One of them is Marina platform that ran from 2010 to 14, which had the goal to create new infrastructures for wind and ocean energy, including combined devices. So the outcomes were many publications on multi-purpose platforms, but also a lot of data for siting of these platforms and even supporting tools that are available to the public today. The H2 Ocean project was intended to develop one platform combining energy and fish farming together. It came to the conceptual design of this structure that has a vertical axis for twin turbine, some wave energy generators, and a fish farm here in the wake of the wave energy device. And this Blue Glow farm is a recent project that finished in March this year. The objective was to produce more advanced knowledge on the topic, and they came to a prototype, 115 scale prototype test at the sea, which is a platform for fish farming and wind wave energy production. This example here is from a Danish company. It combines wind and wave production. So the wind can be from 4 to 15 megawatt. The platform can be modified. It has also facility to storage of energy by electrolyze and hydrogen storage. And this is intended to be in the commercial phase now. But I don't know if they had sold the one yet. Yeah, I want also to show this example from a publication in Ocean Engineering some years ago. It's an example of a synergic design, which means that here they have a wind turbine, oscillating water column energy converter, and they also put a rain and recovery system to increase even more the cost effectiveness. But I think the most interesting is actually both the oscillating water column and the wind turbine, because they made an optimization procedure for the radius of these turrets, and also the coefficient of pressure drop in the Wells turbine in the energy converter. So here you can see in the vertical axis, it's the radius, and they have like different performance indicators like array power and levelized cost of energy. But what's most interesting to see here is that this is the block that shows the stress in the tower of the basin. So without the energy converter, the equivalent fatigue load during the lifetime of the operation would be more or less 30 megapascals. So it would be like this yellow bar here. But as they install the turrets and start to vary the radius, you can see that with a smaller radius, the stress is bigger than when you have a bigger than 8 meters radius. And that's because wave excitation up to 8 meters grows faster than the resistance to motion by inertia damping effects. And then you can see also this is shown also in the pitch and surge and pitch motions. You can see the same effect, especially for surge. For pitch, it's a bit more confused. It starts to get lower again for very big radius. But okay, then I think I can move to design. So I'll talk about some design considerations and show some of the methodology that have been proposed for this type of structures. I'll talk a bit about siting and construction considerations, station keeping, and design optimization. So yeah, so in general, we want to start from a dominant industry, which will be supported by other industries in the platform. So it's easier to establish from activities that are more established. So for example, if we're going to have a wave and a wind and wave energy converter together, the wind energy converter will probably be the dominant technology because it's been there for a long time. The selection of activities will depend on the resources and the surrounding infrastructure, and not least social and cultural aspects, because resistance from society can be a problem for renewable energy in general. We have to live with the fact that we are going to reach suboptimal systems with the combined solution, because it's very hard to optimize all the activities at the same time. You sometimes can have conflicting constraints and objectives. So a pre-assessment is important to ensure that it's really more effective to have all the industries or activities combined in the same platform than having independent platform optimized for their purpose, operating in symbiosis. We don't have a lot of background with these platforms, so unexpected behavior due to unmodeled physical effects have also to be expected during the design. That could be hydrodynamic interactions or unknown couple dynamics. Okay, so to cope with these complications, there have been some design methodologies proposed by these European projects before. So this one is very clear. It starts with a pre-screening process where you do a preliminary assessment of the available resources based on meteorological conditions. And you compare it with thresholds. For example, if you want to have a wind turbine, you want to have a minimum mean wind speed at the site. Or if you want to have fish farming, there is probably a limit in the temperature of the water. And also, at this stage, you're going to determine the feasible sites. Or if you have a number of sites that you can use, you're going to determine which industries will be embarked in the platform. The second phase, or second step, is the preliminary designing of single-purpose platforms for each of the technologies that we're going to install. So here, you can make a more detailed selection of the energy harvesting technologies that we're going to use. It's the time also to check for any legal constraints and to start to think about the solutions that you can have for multi-purpose platforms. The third step is a ranking. So first you create a list of criteria based on maturity of the technology, environmental impact, risks, etc. And then you call a team of experts with different backgrounds. So not only engineers, but also economists, social scientists, biologists. And this team of experts, based on the criteria, will make a ranking of all the solutions and see which of them are the most viable for that purpose. And finally, the last step is to start with the preliminary designing of the platform. So we are going to have the final determination of the site and start with the sizing layout and operations planning. Okay. Yeah, the preliminary design starts with some candidate layouts. So the dominance technology will be the most important in the arrangement. They require a capacity production for each activity is an important factor here. And then you make incremental changes on the dimensions and the layout until we reach a good configuration. So the parametric design consists on modifications of the dimensions with increments. You always want to satisfy the weight buoyancy balance because it has to float, but also want to ensure that limit ranges for the initial periods and metastatic heights are satisfied. It's important in this phase to include some good estimation for added mass and couplings for determining the periods. And here, I think I found this example that I found very interesting. So in the design of the Blue Grove farm, they were here looking into this, here, the walls of this caisson platform. So these yellow lines here are the cross-section of the walls. They started with this rectangular cross section, and they got to this expression for the period in heave. But in this expression, they find that it's impossible to get a natural period in heave away from the wave frequency range unless they use a very, very large volume for the width of the cross section. So then they moved with this different configuration. So here the water plane area piercing the surface is no longer changing with the width, and then they could vary the width in order to get the desired natural period. Challenges that we're going to meet in this process are that we don't know what are the limits in natural periods and inclinations for all these platforms because they are very innovative. We have to model with a model of physics. So for example, if you have these wave energy converters appended around the platform, they can affect the flow. And they have, if you have, for example, a moon pool, you can have free surface effects. And these unmodeled couplings may produce deceptive period estimations. So you can have some bad surprise in the future. So here, the way to cope with this is to, as long as possible, extrapolate ordinary operational range that we're used to from offshore industries, and also design constraints for that we normally use for single-use platforms. And always iterative procedure and model testing is very important at different conceptual levels. Regarding material, steel is very popular in the offshore industry because it's reliable, it has good quality control standards, it's flexible and ductile. But for the size of these platforms, it may start to be more interesting to use concrete, which has extended lifetime and is not constrained, for example, to thickness of the steel plates, diameters of pipes, those things. During the design process, we have started to think about limitations in the shipyard. So dry docks, they have a limit in draft and breadth. And it's very important to have a network of suppliers close to the construction site. And it's also important to think on the transportation to the site when you're planning which shipyard you're going to use, because towing is a risky operation. And we have seen vortex-induced motions for cylindrical structures being towed to the site before. Okay. Siting. So the choice of the place where the platform is going to operate starts with the general requirements for each of the industries. So we have to find a place where resources are available. So if you have enough wind, enough wave, and enough installation. Also, water depth is very important because that governs the mooring design a lot. Temperature, salinity, if you're going to go for fish farming, extreme phenomena, and logistic benefits and challenges. So if it's close to harbors and to maintenance hubs. But a site will not always be optimal for the activities. So again, if we start with a main industry for the platform, you might want to privilege that industry and then choose the optimal site and check for the possible uses for the platform together with the main industry. It can be a very confusing process to find a good site because you have a lot of requirements, a lot of parameters. So for example, wave height, wave period, meaning speed, directionality. So for this purpose, there are some supporting tools based on the geographical information system technology. Marina platform created one public tool for this. So basically, what the systems do is to start with the large volume of data, and then as you set your thresholds and your constraints, it will swipe the database and find what are the possible sites to be used. One thing that's important here to think is that the correlation between the environmental agents can be as important as the parameters themselves. So for example, with a wave and energy device together, it may not be necessarily better to have correlated agents, but instead you want to have the wind and a swell system, because then the swell is not correlated with wind, and you don't have the peaks of productions at the same time. You can have more smooth energy output. There is also systematic procedure for siting proposed in literature. So first you find all the relevant parameters and the thresholds, ranking, and in a secondary step, you go for criteria which we have less confidence with due to lack of background with this type of technology. and that can involve logistics, environmental impact, shipping traffic. And the last case is to go for case studies. Here we're going to go for a detailed or analysis where you can have, for example, the outputs of the systems, and you can really check if the site is adequate. When it comes to station keeping, we want to avoid the platform to drift away. So a mooring system normally is a combination of chain and polyester lines, which could be catenary system, taut or tension legs. If the heading of the platform is to be constant, you can go for a spread mooring system, or you can go for a single point mooring if you can allow the platform to weather vane. And the mooring system is more adequate for permanent systems. But if you design a platform that's going to operate for shorter spans of times and in deep waters, it may be the case to start thinking on dynamic positioning, with the use of thrusters to automatically keep the platform in position. They have, of course, some worries with reliability, redundancy, and maintenance, and they are noisy, so probably not very adequate for fish farming facilities. And you can, of course, combine both and use the DP system to reduce loads in the mooring system. That's also possible. One of the most popular systems for mooring design is catenary, when you can have some excursion. So, well, the main requirement is to allow the excursion in a period, and the restoring will be provided by the weight of the lines. So basically, it's a function of fairly to seabed distance and pretension. You can combine the chain and polyester segments to have a lighter final system, and you can use buoys and weights to force the geometry and optimize the restoring for less chain and polyester. So design optimization is the last part in the design in this presentation. So it basically means to vary the design variables systematically towards reaching optimal design, which translates into minimization of the objective function. So for example, if you have a semi-submersible, you want to vary diameter and draft. So your constraints would be the weight buoyancy balance. It's a quality constraint. And you probably have limited range for initial periods, which would be the inequality constraints. For multipurpose platforms, you probably have many different objective functions. So here we're talking about multi-objective design optimization. We have gradient-free, gradient-based methods. Computational costs can be very high for optimization, and which normally make people to simplify the problems to have quicker process, but that can be a bit dangerous with these multipurpose platforms, because we might not know which effects are allowed to be disregarded. And problem formulation and convergence are very complicated, so it's not so straightforward. Okay, now when it comes to analysis, I'll talk about modeling. We discuss frequency and time domain methods, model testing, coupled analysis, and then environmental modeling and structural life assessment. The objective with modeling is to represent the dynamics of the system with mathematical models. And first thing to choose here is the level of complexity, which is the number of degrees of freedom. If you have a rigid or flexible body, the nonlinearity is involved, hydrodynamic effects, couplings, and all the controllers that can affect the dynamics and the performance of the system. Some common assumptions that we use for one platform for one purpose cannot be adequate for multi-purpose platforms. So for example, will the fish cage or wave energy converters affect the flow? Or if the wind turbine will affect the dynamics of the platform? If the platform is flexible enough to affect the global dynamics? So recommendation here is to go slowly, increase the complexity gradually. Here's an example of what can happen, for example, if you have appendages around the platform that may change the total water plane surface with time. So for the first two cases, you probably won't have a change in the cross-sectional area piercing the surface. But for the three last cases, you see that there is a risk that the wider cross sections can cross the surface, and that would lead to nonlinear hydrostatic stiffness and could cause, for example, material instability, which is characterized by large amplitudes in different periods. So that's only one thing to consider when you append other structures around the platform. When it comes to hydrodynamics, it's always important to check for the influence of viscous effects, because that could reduce the validity of what you get from potential theory. For secondary loads, I think the most important to say here is that dim approximation can not be very accurate for these devices, either because the neutral periods are shorter or because the water is not deep enough. Some frequency loads are important if you have neutral frequencies above the wave frequency range. Morse equation should be used with care because you can have diffraction effects that you wouldn't see for more or less similar offshore structures. And there is also dependence on KC number. When it comes to nonlinear effects, it's hard to list all of them, but I can think about steep waves, wave run-up, and green water. So it's always the case to bet on model tests and use CFD for both validating and calibrating the models that we have. For some applications, it may be the case to model the structure as flexible. Then you can get the sectional loads directly from the analysis, but also it's necessary when the flexibility of the platform affects the global dynamics. So here we can choose between model superposition or finite element. And there's a discussion about computational costs, if software is available, if it's straightforward to determine the mode shapes, if the pattern of the load is complex or not. And then we come to distribution of the loads over the whole. So we can use Morrison equation, or a more sophisticated approach would be distributed potential theory. It's more complicated also. And hydroelasticity here would be the two-way interaction between structural deformations and the surrounding flow. So meaning that the flow will deform the structure, and the structure will also affect the flow, and it's back and forth. This is not expected to be a big problem for concrete or steel structures with dimensions in the order of magnitudes of tens of meters. For model testing, this is also it's normally a very important step in the design of any offshore industry, but for multipurpose platform, it can be more important and more complicated. So first, fruit scaling, which is a typical approach for many offshore applications, will be questionable for platforms that have slender structures appended to it. But also, it can be the case that you have different scaling laws in the platform. So I used here the example of floating wind turbines, which are actually single-use platform devices. But I have two different tests here. The first, we have the hydrodynamics scaled with fluid scaling, but the aerodynamic loads would scale with geometric scaling, keeping the tip speed ratio constant. So what we do here is to apply the loads at the top using a system of cables. But in the bottom, they do the opposite. Here, they kept the aerodynamic model with the appropriate scaling law, and the motions are imposed and simulated and imposed on the bottom. I think this type of procedure will be more and more required for multipurpose platforms, because you can have even other scalings that can't just be left out. If the platform is too big and elasticity is important, that can also be a complication, because it's quite challenging to model bending stiffness in tests. And indoor facilities may start to be too small for some of these concepts if they are too large and they can't be scaled too much. So full scaling testing is probably a step forward for this type of industry. Okay, regarding frequency and time domain methods. So frequency domain is quicker, but if nonlinearities matter, the accuracy can be very reduced. So basically, we start with a forcing spectrum, use a transfer function, and get a response. But finding the transfer function can be very challenging if the system is quite complex and has many degrees of freedom. Alternative is using time domain methods. They are accurate if your modeling is good. They can become very expensive and have numerical stability issues, especially if you have a finite element together. And one advantage of time domain methods that you have many off-the-shelf options available, which may not be the case for frequency domain. Coupled analysis is a type of simulations which you do when you have different subsystems interacting with each other. So for example, if you have a wave energy converter and a float wind turbine, so the converters can affect the motions of the float wind turbine, which will also pitch the platform and affect the performance of the energy converters. Or if you have very large bodies, but also slender elements, so you want to combine rigid bodies and finite elements, so each of them interact with the dynamics of the other. For offshore industry, the state-of-the-art approach is what we call aerohydroservoelastic analysis, which basically just means to have all the important loading at the same time and interacting with each other. And it's not very complicated to add models for wave energy converters and fish cages, for example. So we can use off-the-shelf software and just implement the load models if needed. Okay, environmental modeling is very important in when it comes to analysis. So to characterize the wave system, we normally speak about wave significant height and mean peak period and incidence direction. Appropriate spectrum formulation is normally given the meditation data also. If directionality is important, you have to go for short crested seas and use some of the spreading energy functions. Yes, and the discussion that may be new for these systems is whether you have to model wind seas together with swells. Because, as I said, if you're going to combine, for example, wind and wave, it can be interesting to have swell systems. And yeah, so for example, this picture is from Wave Watch, where you have for the same site 1 wind sea and 3 swell systems. So for wind, we normally need to have the mean wind speed and direction, turbulence intensity, wind shear characteristics, coherence, and wake effects if you have more than one platform in the same site. And with current, the approach is normally to have a profile of current velocity and direction versus water depth. So Metuchen data is a database describing waves, current, and wind for a given site. There's a lot of public available data from previous Euro projects, but also from Wave Watch that's provided by NOAA from the US government. Normally, we assume that a short-term condition will last for 1 to 3 hours. So this data can be given in this time span. So wind waves, they are in general correlated with wind velocity, which encourages us to use a long-term joint distribution between wave height, period, and velocity. This kind of distribution is nice, useful, for example, to weigh the load effects for fatigue analysis from the different beams in the scatter diagram, and also to find environmental contours for extreme loads and motions analysis. Misaligned environment can increase complexity. So a collinear assumption of wind and waves and current may not necessarily be conservative. That has to be checked for each type of concept. And swell waves are normally not correlated with wind, but they normally propagate in a preferred direction and are highly affected by seasonality. So at least in the initial design process, you can normally assume swells to propagate in just a few directions. And current is also not normally correlated with wind and waves. So it's again the case to make a screening of different combinations and find the worst case scenarios. So fatigue analysis is about accumulation of damage at different places in the structure due to cyclic loading coming from waves, wind, machinery, vibration. Yeah. It's normally the case to select the more dangerous spots would be welded connection and sharp corners in the hull. For steel structures, it's normally at least a good start to use the linear damage accumulation hypothesis from Pomegranate Miner and SN curves that are available in standards. So the procedure here would be to start in a scatter diagram where we have the combinations of significant wave and height for each mean wind speed. So what to do, for example, if you have a wind and wave energy platform, you have one scatter diagram of this for each wind speed. you simulate all the relevant beams that have some threshold in the probability of occurrence. Then you get the damage from each of these the simulations. You normally want to have several realizations of each condition, and then you make a weighting procedure with the long-term distribution. It's important to say that simultaneous operation of different machinery, they can impose cyclic loads that will superpose to each other, and this can affect the associated damage. So for extreme analysis, it's about ultimate loads or extreme loads and motions when you have a combination of wind, wave, and current. That can provoke not only material yield, but also, for example, buckling or excessive motions in machinery that can damage wind turbines, the converters. It can be also detrimental to the fish species being produced if you have a fish farm. It's important to mention that extreme loads are not necessarily happening under extreme conditions. So, for example, if you have a wind turbine in the platform, the biggest load will probably be around the rated wind speed, probably the biggest wind load, and that won't be always correspond to the most extreme condition, most extreme waves, for example, but that can be the worst case, especially for bigger structures. Okay, so basically the procedure here would be to select a number of load cases and run a number of simulations. So, for example, usually 20 simulate realizations for each case is a good number to start with. For each of the simulations, you are going to get the extreme and fit to a distribution, where the Gumbel distribution is normally suitable for offshore operations. Other methods to avoid the amount of simulations could be, for example, peaks over thresholds. So you set a threshold and measure the number of peaks, and then distribute these peaks on the distribution. There are different approaches. Yeah, accidental limit state is about atypical loads and events that can affect the structural integrity of the platform. For example, ship collision, or if one of the mooring lines breaks and the platform loses position. It of course depends a lot on the type of equipment and this industry that you have. So if you have a wind turbine, you're probably going to screen for wind turbine faults. There is fire hazard for all kinds of equipment. So this is also something to screen and risk assess during the design phase. And of course, if the platform is manned, which is the case probably for fish farming, then the tolerance to this type of accidents is much smaller than if you have an unmanned platform. And it's also important to consider serviceability limit state, which is cases that the platform has to stop operating and producing depending on limits during the operation. This also depends a lot on the type of platform and should be considered during the design phase. So yes, multipurpose platforms can be really very cost-effective and save resource and construction efforts, but its viability is subject to the performance, costs, and environment impact in comparison with independent platforms operating synergy. If resources are available and correlated, because as I said, if you have high wind and wave peaks at the same time, they won't be very helpful in power output. Existing logistics support networks and construction facilities, if the transport is viable and those things. And design of multipurpose platforms can be more complex than single purpose platforms because we don't know performance criteria. We don't know, we don't have a lot of background with this type of platforms. So it's good to lean on the systematic approach that you can find in literature, at least to have a starting point. And existing numerical models can and should be adapted for multipurpose platforms, but you have to be careful with hydrodynamic interactions and couplings and nonlinearities and any other effects that we don't know. So always use a lot of iterations, model testing, and CFD. Yeah, so this was it. So, thank you.
So thank you very much, Carlos.
Okay.
It's working. All right, so thank you very much, Carlos, again. There is no official requirement for questioning of the trial lecture, but I would like to ask the committee if they would like to have clarification. No specific. Professor Colo, would you like to have any clarification?
Yeah, I'd be interested in hearing Carlos' opinion about one particular point. So I'm aware of the fact that this was just a brief investigation to prepare the trial lecture, and your PhD was on something else. But I wanted to know what is your opinion about this question. So, as you have also shown in your presentation, multi-purpose platforms may have some advantages with respect to a single-purpose platform under certain conditions. Why do you think that there are still no commercially viable or proven multi-purpose platforms out there?
Actually, the only one that I found in my investigation, my research for this lecture, that was closer to be commercially available was this FPP by DTU, because they have a website with investors and they say that the system is already patent and has got a high technology readiness level. From all the others case that I found, I didn't see any case that's already in real scale operating for some time and already has proven its viability. So that's the reason why I say.
No, I know that there are not, but why do you think this is
why the reason?
Why no one has found a way to make them economically viable and proven?
Yes, well, that's a good question. I think one of the reasons that when people start to think about these platforms, they might meet all these challenges regarding adequate models, and they start to question themselves, like, should we really go for a combined system or for a combined solution, or should we go for independent systems operating close to each other? Or yeah, I think that's it's normally an economical reason, because it takes time for a new solution to become viable and to become cheap enough to be produced in commercial scale. And so if people can reach a good enough solution with a single purpose platform, they just say, okay, I'm not going to invest on this right now. So I think that's one actually the advantage of having so much funding for public projects on that, because I think there's a lot of development to be made before we can prove in the industry that this is really viable. And actually we have to prove that this is viable, because we can end up never showing that.
And do you think that the challenges are limited to techno-economic challenges, or do you think there are other aspects to be considered as well?
That will depend a lot on which type of activity you're going to combine in the platform. So for the solutions that we saw so far for wind and wave, I mean, in my PhD, I looked a lot on wind energy, but I didn't study a lot of wave energy. But my impression is that in order to optimize output from wave energy converters, you actually want the device to move as much as possible with the waves. And that's normally something that you don't want for a wind turbine. So if you want to combine this device in a single platform, you're going to be suboptimal for wave energy, for example. And then it starts to be the question, like, wave energy is normally considered less efficient. So if you're then on top of that, limiting the motions to have less damage to the wind turbine of the platform in general. So is it really worth going for this combined solution? So still has to be proven. It's not only a question of the technology maturity, but also if that's really possible to, even with the best technology, to have something that's cheaper than having independent platforms. So I think that's very case to case. But for example, for the Blue Growth platform, maybe having at least the wind turbine with the fish cage would be a very interesting solution, because then you have supply of energy directly from the wind turbine to the fish cage, to the fish farming facility. and you don't have to lean too much in power cables and those things. So this type of solutions where you have one activity supporting the other might be the first to progress and become commercial.
Okay. So you see a gradual introduction, not starting with something too complex or too different from what is out there, and little by little progress to something more complex in a way. So that makes a lot of sense. So if you think about floating wind turbines, that is the core of your PhD. We probably couldn't have jumped from onshore wind turbines into floating wind turbine because those would have been perceived as too different, too dangerous, too risky, too expensive. So the key has been to literally dip our toes in the water with fixed wind turbines very close to the shore and in very shallow waters, and then little by little see, oh, can be done. Let's go a bit further. Until you reach a point where you cannot do any longer fixed wind turbines, so do you floating. So I agree with you that in the sense that for the time being, the jump from what is done at the moment and what are those multipurpose platform is still perceived as too big and too risky. So more fundamental knowledge and public funded research is needed. But also think about beyond techno-economic, from a social and a legal point of view. There are very well established frameworks in terms of how to certify a wind turbine, how to classify and certify a wind turbine, therefore how to get some insurance on your asset based on the certification. For a multipurpose platform, there's nothing of the sort, and it may be completely cumbersome and very difficult to envisage a legal framework for a wind wave device or a wind aquaculture device. So think about beyond techno-economic as well. I have another question if I have the time. Amir, is it possible?
No problem. No, the discussion getting warmer and warmer is okay. No problem.
Okay.
Yeah, please.
So in your slide number 50, you show that from the scatter diagram, you can have, yeah, I'll leave you go to the slide. So for fatigue analysis, you have a scatter diagram that gives you the joint probability distribution of HS and TP, and also this can depend on the wind speed, obviously. So you basically can weight the importance of each C state or each combination of HS and TP. The question is that in theory, you should basically run an fatigue analysis for each one of these combination and then weight their contribution to fatigue according to the number of occurrences. And then you can kind of derive what is going to be the total fatigue accumulated by this particular platform. But these may mean hundreds of simulations, also taking into consideration the fact that you need to do the same simulation more than once because of the stochasticity of wind and waves, and therefore use several seeds. My question is, if you are in a kind of a optimization framework where you cannot afford to do hundreds of simulations for each iteration of your design, trying to find the optimum solution, how do you rank or select which one are the most important C states contributing to fatigue?
Yes. So if you are in a very early design phase, you might want to get for the most probable combination, and also a few others that give some level of joint probability for each wave, wind and wave conditions. But then as you move towards a more detailed phase, I would lean a lot on sensitivity analysis like was done by Kvit and Moen 2 years ago, where they did this for a float wind turbine. But basically what they did was depart from for this more complete scatter diagram and narrow it like in terms of number of simulations, number of realizations, length of simulations, and what would be the probability threshold. And so it may be the case that you run this once for one platform dimension that you think is representative. And then when you reach to a level where you find a good convergence of the fatigue result with a tolerable number of simulations, then you can assume that even if you change the dimensions of the platform a little bit, you can still use the same criteria to proceed with your optimization.
But will not that limit the range over which you can vary your parameters? Because obviously, if you wildly change your parameters or the shape of your platform, you surely know the work done by Erin Banczewski and Eggset and continued by other colleagues at TNU, where they try to investigate, let's say, unconventional shapes for spars or other platforms. So how can you be sure? Can you be sure that this sensitivity analysis done for one particular platform is then applicable to the other more unconventional shapes?
Maybe by doing this initial screening to different limit for the ranges for the dimensions. Mm-hmm. So, for example, if you have a semi-submersible, you say, okay, I will do this initial analysis for a column with 10 meters, mm-hmm. and then I'll run another for column with 15 and a column with 8. And then you check if this analysis changed too much between them. You say, okay, inside this range, I can vary a lot. But if it goes outside this range, then I have to run it again.
Okay. So it's a kind of pre-processing step where you try to get a sensitivity of how much is the impact of the parameters on this sensitivity analysis.
Exactly. And that's probably very time consuming, but that's how it is.
That's it from my side.
Thank you.
Thank you very much, Professor Nilsson has a few comments, please.
Just a short follow-up. You have mentioned the combination of wind energy, wave, and fish farming. But in your literature review, did you come over any other technologies or energy converters or whatever?
Yes.
In your
very to the top. Virtually, maybe you can navigate more easily. Okay. So this one.
Yeah, and maybe the follow-up on that, what kind of combinations do you see as most realistic?
I like the combination of wind and fish farming for the reason that I said to Mauricio, because they are two more or less established industries. So you're left, and you don't expect aerodynamics to interact with each other so much. But the main advantage is that then you can have like a more guaranteed supply of energy to the fish farming, provided that you can store the energy from the turbine. So that, I mean, if I would invest in some technology, I would start from this combination where I have two industries that are more established and one can supply the other. Here for this one, for example, I don't know how feasible it is because I don't know anything about grain recovery, but what they propose is to just like append something that's not going to affect the dynamics a lot for a wind turbine, and that could potentially increase the revenue. So yeah.
So thank you again, Carlos. Thank you very much. Thanks also to the audience. Please be back here 1:15. Professor Kollo, please stay with us. We will move to another room. Also, the audience, they join online. We will be back 1:15. So thank you again, everyone.